Bueno, es un placer tener hoy con nosotros a Víctor Verdugo. Víctor Verdugo es profesor aquí en el Instituto en la Pontificia Universidad Católica de Chile. Víctor tiene su grado de grado y su magíster en Ingeniería Matemática en la Universidad de Chile y su doctorado entre la Universidad de Chile y la Escuela Normal de Superior. Luego hizo un postdoc en la London School of Economics y también fue profesor en la Universidad de O'Higgins antes de unirse al instituto. Trabaja en optimización, algoritmos de aproximación para optimización en grafos. Y bueno, lo que nos va a hablar hoy, pues vemos limitados, por favor.
Thanks a lot, Federico.
Y la charla va a ser en inglés.
Yeah, in English. Yeah, no, thanks a lot for the kind introduction. Yeah, today I will tell you about a recent work that I did with Sebastián Pérez Salazar. Some of you know Sebastián. He's a professor at Rice. And it's about profit inequality, but it's a different model. Okay? So it's, for you that have seen the problem before, it's a different model than the classic question. So I'll tell you about this. Okay, perfect. Let me tell you about the setting. Imagine that I have the following situation. You want to, let's say, provide a service, or you have a house, for example, and you put it on the market. So you want to find someone for renting the house, and therefore, what you see in the process of finding the right person is that sequentially, people will come, they will be interested in the offer, right? And they will have a valuation for this. And at the moment of arrival, you will see the value of the person for this. Yeah. But at that point, you have to take the following decision. Either you select the person, so you say, well, you know, like this is I think I'm happy with this person, so I will rent my place, and I will tell you for how long. Okay, so then I will tell you, for example, okay, so I'm happy with you, and I will rent the place for 1 year, okay? 12 months. Okay, so you have to commit to the person, right? And for how long? So for certain period of time, okay? And you have to commit to that. What does it mean? It means that if after that person, after you committed, someone comes, okay, and has a greater valuation for the place, then you cannot take it, okay? Because you already committed for 1 year with the other person. Okay? So this is the problem that you have to solve. Okay? Then again, let me repeat. So you sequentially observe values. Okay? I will assume that these values are random. They are all drawn from the same distribution, and they will be independent, okay, across the periods. And then I will compare the quality of a solution that I would give for the problem respect to what a profit would do. Okay? So what would be a profit here? By a profit, I mean someone who has access to all the values up front. Okay? He has full knowledge in that sense. Okay? And therefore, what would the profit do? Well, if you see all the values at every point in time, you will know who is the best so far, right? And therefore, you will stick to the best so far. And this is what you will do, right? And this is why in the value for the profit, right, or the benchmark, I will call it benchmark as well during the talk, what you do is at every period, so you just keep track of the best so far, and you compute the expectation of that, and you take a average. Right? So at every moment, I know who is the best, and that would be my solution.
So so you choose TI however you want. So there's no restriction depending on the person.
There is no constraint. There is no constraint. So at the moment of selecting someone, you decide for how long, and after that period finishes, then you can take someone else, and again you decide for how long.
Okay. And you're gonna still keep the same person, no? You cannot.
You could keep the same person forever if you want. So for example, I could say if I have n periods, and now I receive someone who looks really good, then I could decide to take it until the end of the period.
Right, but if you decide to take it only for a few time steps, then you cannot retake it.
I don't know, then it's passed. Okay, but then after that period finishes, you can take someone else that would come after that period. But during the period of time in which you are blocked, then you cannot select anyone else. So then you have to let everyone pass in that period. Yeah.
What about the first period? Are you allowed to skip for the first period and get 0?
So no, for the first period, so what you say essentially is that if I let that person pass, right? I take the value for one period, but then I don't take it, right? And let it go. Or I could decide to take it for 3 periods, and then I'm blocked for 3 periods, and then I can take a decision.
Okay, so the first one, you take at least 1 period, and maybe just 1.
Yeah. So, and then from that moment you decide.
The other question is that, just a notational question.
Yes, yes.
Proceeding backwards?
Yes, good point. So here, I'm assuming that I have I units to go. Okay, so then in the picture here, I say if I have I periods still to go, so if there are I periods that remain to solve the problem, then I will accept the value for Ti units of time. Okay. I'm assuming it's at least 1. So this is for exactly that situation that you say at the beginning. Like I have to take for at least 1 period if I want to be competitive. By saying I'm done. So then I have to select it for at least 1 unit of period. Okay. And then during Ti units of time, I don't do any other. I don't take any other decision. I just skip everyone that could come.
So in fact, here Xn is the first one.
Yes.
So you're numbering the variations in reverse order.
In reverse order. For this part, I mean, just to. Yeah. Is the model clear? Yeah. Okay. So everything here will be IID. Okay. So then all the evaluations are identical and independent. Okay, and how do I measure the quality of the solution? So I will study the competitive ratio. What is the competitive ratio? I will look at the value of the algorithm. Yes.
So the algorithm will decide at every I,
Yes.
observe its I, and decide Ti.
And you decide.
That's it.
That's it.
And the Ti only depends on the number of remaining periods and the value that you just observed.
Exactly. And you know the distribution. So you can also use that for
the future.
Exactly. So you know the distribution and you can use all that to compute the TD. So therefore, any policy would look like this. So you say, here I will select this thing for this many periods, right? And then in between, I don't select anything. And then after that period finishes, I can take something again. Right? Okay, and then the quality of the solution will be measured according to the competitive ratio. So I look at the value of the algorithm. Right? So I mean on expectation, how well I'm doing with the algorithm over the benchmark, which is under, let's say, full knowledge of the value. Yeah, and this is the ratio I look. So the larger the ratio, the better the algorithm. Good. Okay, so this problem is, I mean, not exactly the same model of perfect inequalities that people typically look at. But there is a long line of research in this thing. Yeah. So typically in the classic question, I can tell you briefly what is the classic question is, so you see values sequentially. Yeah. Again, you can assume that they are all IID. But at any point in time, so once you see the value, you decide whether to take it or not. Okay? And if you take the value, then you get that reward. Okay? And that's it. And game is finished. And therefore, any algorithm there has to decide when to stop. So you have to look for a stopping rule. But again, you would compare against the optimal solution, which would be take all the values, compute the maximum, and take the expectation of that. That would be the profit in that setting. And this is the classic profit inequality question. And in the IIT setting, we understand very well the competitive ratio. So it's something like, you can recover something like 74.5% of the optimal solution in the IIT setting. But this model is a bit different, right? Because here I'm taking decisions over time, right? And once I take a value, I keep gaining reward, right? From that value that I took. So in the classic question, it's a one-shot question. So you select a value and you get that reward, and that's it. So this is more like an over time question. So you keep getting reward once you take a value. Okay, and for this setting, there are a few results known. Yeah. So I think that the problem was introduced recently. Yeah, I would say that not more than maybe 3 years ago. Okay? But it has been studied especially in setting when you want to model procurement situations, right? For example, imagine that you want to provide a service. Yeah. Again, the service has to be provided during the full time, during the full period, right? But at any point in time, I mean, you can decide, well, I will provide the service using this option, yeah, but only for 1 year. And then after 1 year, I'm allowed to change, right? And I could provide the service using another option. And again, you have a version in which you would like to maximize the value of the algorithm, but maybe you want to minimize the cost, right? So both versions have been studied. And for the max version, which is the one that I presented here, there are essentially 2 results. So, and they are recent from last year, essentially. In one of them, yeah, which is a result by Adams et al., they prove that with a single threshold strategy, what is a single threshold strategy? It means I will put a bar, right? So I will set a threshold. And then once I see a value which is over the threshold, I will take that value and I will take it forever. Okay? So it's a very simple policy. So you say, for example, okay, my threshold will be 1,000. First time I see a value over 1,000, I will take it and I will take it until the end. And this is my policy.
And what do you do before that?
Let everything back. Well, you sell it for 1 unit.
Just for 1 unit until you observe something.
Until you observe something above 1,000. And that policy, very simple policy.
So just a question. So suppose I observe a value which is 10. I commit for 1 unit of time, and then the next period I observe a value of 5.
Yeah, then
Can I keep the 10 for 1 extra unit of time, or I have to?
No, you have to let it pass.
The other guy is gone.
You have to let it pass. Yeah, because if you in this policy at least, yeah, so I will take everything for 1 period or 1 unit until I see the large value. And then I will commit.
But I thought it was a constraint of the setting. Right?
It's a constraint of the setting. You have to take it for 1 unit.
And if you just take it with 1 unit, after the 1 unit, the guy is gone and then you're good.
Yeah. Is it clear, the policy? Yeah.
Just wondering how important it is to know N in advance,
No N?
and or whether actually you can play this game forever, for instance.
That's a good question.
And then you can hopefully say something about the limit of.
I think you have to assume something about N.
Is the threshold selected based on that?
The threshold, yes. 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 So I know N. Yeah, but sometimes even if you don't know N, you can say something. But my impression is that, for example, in the classic profit inequality, if you don't know N, you cannot do anything. And even if n is random, you cannot do anything. I mean, unless the distribution of n is very particular.
Wait, but that's because you're aiming for an absolute constant ratio, right?
Yes.
Because I'm guessing that 1 over log n should be.
Okay, there
that's
it might be.
equal, right?
Yeah, there it might be. I agree. Yeah, but if you aim for constant competitive ratio, I think you need more information. Yeah, so here I'm assuming that, I mean, all the things that I know here are, I know n, and I know the distribution. Okay, so I know the distribution of the valuations. This is known for me. Okay, so yeah, so previous results. So with one threshold, you can get something like 39.6% of the optimal value. Yeah, not bad. With a single threshold. And they also show that if you use a more complicated policy, in which you dynamically change now the thresholds over time, then you can get something like 59.8%. Yeah. But for large n. Okay, so at the beginning it will be worst, okay, but it will converge to that value, which is roughly 60%. But then there is an upper bound, yeah, that they also introduced, which is 1 over the golden ratio. So you cannot get more than 61.8% of the optimal value. And therefore there is a gap, right? So there was a gap.
Bound is just for threshold time algorithm, or
Even the optimal algorithm, the dynamic programming policy. But I will talk about that in a few more slides. Yeah. But this upper bound is for the best algorithm that you could pick, okay? And the best algorithm will be ADP, which is not complicated to write. I will show in a few minutes. Okay, so then you have a right? So essentially, you can do between roughly 60% asymptotically and 61.8. Yeah. But with a single threshold, you can do like 39.6. This is what they show.
And that's tight.
This
The single threshold is like that.
No.
Value is tight for now.
not tight. Yeah, not tight. It's just a lower bound, but they didn't give any upper bound. And the other result that was known before, it's other recent result from this year, in which Andres Christian, Siga Loren, they, for a different model, right? Not exactly this problem, but this problem is captured by the setting they introduced. They prove that you can achieve a 1/2. You can guarantee 50%.
Which type of one?
It's a bit different, not a single threshold. I mean, it's not so complicated, but it gives you a half, for sure. While this other result, for example, this is asymptotic, so therefore small n will not give you. Yeah. Okay, so these two things are easy papers, so one last year, one this year. Okay, and what do we show? We go here. Yeah, so these are our results. So we have essentially two types of results in two different regions. First, let me talk about the few threshold region. Okay. What we show is that if you use a single threshold strategy, then you can achieve 56.7% approximately. And this is tight. I can.
Nothing 30 kilos, right?
Is
minus.
yes. So what we get is. I don't want to mess it up here, but these are the lights.
But if you write, you can see.
You can see.
Yeah,
Okay.
we can see.
Yeah. Okay, so for one threshold, the value is 1 plus e to the minus 2 over 2. And what we guarantee is this times something which is like 4 over a plus 1, something like that. Okay. And this is the value which is 0.567. Okay. And this is for one threshold and it's tight. So you cannot do better than this.
It's tight for everyone.
It's tight in the sense that you cannot do better than 1 plus e to the minus 2 over 2.
Oh,
So it's tight. Yeah. So for one threshold, this is the answer. You can get 56.7%. Yeah. And then if you do a bit more, yeah, because using the same idea, we can provide guarantees also for more threshold. Yeah? 2 or 3, let's say. With 3, you can already surpass the 60%. Okay, so then I'm showing the result with 3 threshold because already with 3 threshold, you can surpass the guarantee, the previous guarantee, yeah, that was using many thresholds. Essentially, they were changing thresholds all the time.
How was the upper bound again? What's your point?
So the upper bound is one with the golden ratio, which is basically the upper bound is 0.618, more or less. So with 3 threshold, you are already beyond the 60%. Okay. And of course, if you keep adding threshold, then you will do better and better, and eventually you will do at the optimal algorithm. If you can change the threshold at every time, then you can do as well at the optimal algorithm. Okay, and then the second result is about the optimal algorithm, okay, about the DP. And for the DP, we provide a full characterization of the competitive ratio by using a convex optimization problem. Okay, what does it mean? It means that for every n, I can write a convex optimization problem, which is not too complicated. You solve it, and this is the competitive ratio, the worst case competitive ratio, over every possible distribution.
But it doesn't tell you what is their policy.
The policy is the DP.
The DP usually.
No, I can compute the policy. I can give you the policy. Yeah. Yeah, because the program will give me the optimal threshold. Yeah. So that's it. And yeah, and actually the curve, I didn't put it here, but essentially as a function of it, then the competitive ratio, the worst case. So when I say competitive ratio, I'm taking the infimum over every possible distribution as well. Okay. So the worst case over every possible distribution. Here, if you have the 1 over the Gondel ratio, then it's something like this. So it gets worst with them. Okay. Then what we did is, well, if you take the convex optimization problem, you write down the optimality condition, then you will get a system. And then if you let n grow, that system will converge to a nonlinear system, yeah, of differential equation, which is that system that I leave there. And when you compute the constant, okay, for this system to have a solution, which is this value here, this is exactly the 0.618. Okay. And here I already tell one open question that we don't know how to answer, but we tried. But I don't know how to solve it. I would like to show that this is exactly 1 over the Golden ratio. So take that differential equation, and the first value that you have there, the 1 over gamma, this is a parameter. Okay? And I would like to show that for that ODE to have a solution, it should be the Golden ratio.
Like if and only if you're saying? Like the only gamma for which you have a solution to that.
1 over the Golden ratio. I mean, I can only compute it computationally. I mean, I understand, okay, let me say it another way. So I understand the ODE, but I don't know how to prove that this value is exactly 1 over the Golden ratio. And we tried. I don't know, it might be simple or not, but yeah.
What's the interpretation of y of t?
Of y of t.
Is the limit of what?
Anything. Y of t.
Like you're discretizing time with the step size of 1 over n, something like this.
Yes.
So you're doing
So the thing that
the y of t would be the value.
it's a quantile. So the thing is that for getting that ODE, I already went to the quantile space,
Okay.
and then I'm taking limit. So let me see if I can find out an interpretation of that. I need to.
The quantile over what distribution?
Ah,
The quantile of what distribution? Like the value over time.
No, it's a bit different. I mean, we can talk about that offline, but because you have to do, so the thing is that when you write down the convex problem, I'm changing variables. So I'm using, for every variable, I'm using now not the thresholds, but I'm looking at differences. So then when you go to the limit, you're looking at some derivatives.
Like the difference of the threshold.
Right, so then I would need to keep track of all the changes. So, but give me some time, like after the talk, I can try to reconstruct it.
But it is somehow related to the threshold.
It's somehow related to the threshold, which is a quantity strategy, that I can tell you. But to keep track, but then I will need to backtrack the change. To tell you exactly what it is.
I don't see where the distribution of comes in.
Yeah. Okay, yes, so
That is worst case for the distribution,
in
right?
worst case, yes, in worst case, in worst case. So the thing is that when you solve for particular n, I can give you the worst case distribution for that n, one of them, because there might be several bad distribution, but I can give you one. Okay, yes.
And does this strategy also work when you don't take the worst case distribution over, like the worst case over all possible distributions, but only over like a class of distributions?
Mhm.
You also get some sort of comments programming for the worst case, right?
For the, so now if you only want to look at a subset of distributions,
Yeah, let's say when to constrain, like,
mm,
because maybe you know something about the distribution, so it's not that completely arbitrary.
could be, I'm not completely sure. Because there is a reduction I start to tell you a bit about that, but there is some reduction I'm doing in which, I need some freedom in the space of distribution. So if you constrain the space, after doing the reduction, I might fall out. Okay, so this is why I'm not so sure. Okay, let me try to briefly tell you the idea for one threshold. Okay, and then for the DB, hope I can give you the main ideas of the analysis. Okay, for one threshold, the idea is the following. First, so recall that what I will do is I will set a value tau. And first time I see a value over tau, I will commit to that value until the end. This is my case. So in other words, in my algorithm, if I'm setting tau as a threshold, what I will get is, well, at every period, I have the probability of being above, and before I was not above. Right? So this is exactly the probability of being above, and before I was not. And this is how much I gain for taking that value. Right? Is I will get the value given that is above the threshold for this many number of periods. So until the end. So then this is a lower bound on the value of the algorithm. Okay. So as you can see here, I'm taking only the value I get from the moment I commit. Like before, I don't care much. Yeah. And then, well, you can write down this equivalently using the following transformation. So one typical way of finding good thresholds is by going to the quantile space. Okay, so then you say, I want to set a threshold tau. So now let me consider the value q, which is the probability of being over tau. And now tau will be just here. Let me assume that the distribution is as nice as needed. Okay, you can take inverse, you can take derivative as many times as you want. Everything is continuous. So then the threshold will be just the inverse of f in 1 minus q. Okay. So then I can now write down everything in terms of q, which is a quantile. Now it's a value between 0 and 1. And you give and you get that, so you get that expression. This is a quantile expression. And now let me do one further transformation, which is the following. Assuming again that f is nice and needed, the inverse of it will have a density. Okay? So then I will write down the inverse of f, 1 minus u, as the integral of some function r in between u and 1. So there will be a density for the inverse. And then again, by replacing here, you end up with this expression. And the nice thing about this expression is that now you're integrating between 0 and 1. You have RV here, which is that density that appears from the inverse. And you have here this other quantity that depends on V and depends on the quantile. And so far, I didn't select the quantile yet, so I have freedom, right? I will select the good quantile. But this is a general formula.
So what is A? What is A?
Some function. Yeah, that appears from here. It's not ugly. I just omitted the. But it's an easy calculation. So you go from here to here. Okay, so then this is the algorithm, a lower bound on the algorithm value. Okay, and now let me do a similar thing for opt. If you look at the benchmark, doing the same thing that I did here, right? I can write down the benchmark in terms of the quantiles. And then using that the inverse has a density, I can put it here, and I will end up with an expression like this, which is again an integral from 0 to 1 of RV times some other function g that depends on v.
But
Yeah.
isn't then, like you're assuming implicitly there that the optimal strategy is threshold strategy, right? Is that obvious?
No, I'm not assuming. So
That's the optimal strategy.
this expression for opt is just by computing the expectation of the maximum.
Yeah, okay.
So here in the benchmark, here I'm just doing like the typical
Okay.
expectation of the maximum.
You're integrating the tails for
Yeah.
the.
That's it. Like I'm computing the expectation of the maximum over the value. That's it. And the RIA. And you will end up with this thing. Okay. Yeah, but this is good. Yeah. Why this is good? Because now the algorithm is at least something which is an integral from 0 to 1 of a function RV times something that depends on V. Op is an integral from 0 to 1 of RV times other thing that depends on V. And I want to lower bound the ratio between the two. And I want to select the right quantile. This is the game. Okay, but then what you have is essentially a ratio in which in the numerator you have integral of r times something, and in the denominator you have integral of r times something. Well, the ratio of this thing is at least the infimum of the terms multiplying RV.
So R
Which
is
is the
a
common
density, right?
Hmm?
R is a density.
R is
So the
the derivative.
but it integrates to one.
Doesn't have to.
You don't need it.
Ah, okay, yeah,
No,
yeah, sure,
it's-
you're correct.
I mean, that inequality is true in general.
Yeah.
So I think one easy way to see it is that, I mean, the integrals here, imagine that they are just summations. And I'm taking the sum of Ri alpha I divided sum of Ri beta I. Well, this is always at least the infimum over I of alpha I over beta I. One lecture. You do it for the sums, true for integral. Yeah. Okay, and then just in the inequality. No, but this is great because now I forget about R. This is the thing. Right? R was encoding F. But now with this inequality, I have no longer R. Right? So then I forget about F and I have a uniform bound. And that's it. And now the only thing that remains to be done is picking the right quantile. And you can prove that if you select the quantile to be something like 2 over n, more or less, then we will get this expression here. Well, in fact, so here I'm taking the So this is the value that you would get if you take as a one-time alpha over n, when alpha is a constant. And then if you optimize here, then you get that the right value should be 2. And therefore the quantity is like 2 over n. Yeah. And what you have here is a plot of this function as a function of alpha.
There's two changes of variables that happen already, right? Because you want to set tau.
Yes,
You replace it by q.
by q, and then q,
You
I'm,
replace it by what? V?
and then I'm taking essentially, and then I'm looking at the speed. Like a derivative of the, right?
But what's the variable related to the threshold ultimately, like in the green?
Yeah. Okay, so the quantile will be like 2 over n. Yeah, so therefore the threshold will be the inverse of f in 1 minus 2 over n. This is the threshold. Right. Yes. And that's it. And this is the analysis for one threshold. And again, if I have to, like, summarizing, what is the nice thing about this analysis is that by doing this final transformation, so when you take the density of the inverse of f, then you end up with something where you can use this simple inequality and then you forget about this. And you get immediately a uniform bound. And by the way, you can do the same thing for the classic profit inequality and you will get, for one threshold, you will get the, what you should, 1 minus 1 of it. But it's a simple analysis. And then, well, you can push this analysis for more thresholds. I will not show it here, but you can push it for any number of thresholds. And now the expression will be much more complicated, right? But still manageable. Possible. And if you use 2 thresholds, then you can get something like 58.7, and then with 3 you already surpass the 60%.
This thing you need to solve it numerically, right? And
It
there's
is
no
solved
way.
numerically, so maybe.
So Victor,
Yeah.
I mean, in the analysis there, right, you always forget about how the distribution looked like before the threshold, like, or like, sorry, you forget about the money you're paying before the threshold. So is that suggesting then that the worst case distributions are somehow like 2-point distributions?
So
That you
it
get
is.
0 at the beginning?
Yeah.
Because you don't lose anything in the worst case when you take this.
This is the worst case. Yeah.
Has to be there.
Yeah, I didn't show it here, but the tight example, so for the one where you cannot get more than it, is a distribution like this. And you can construct it and we'll give you the.
Okay, so but then if you constrain your classes of distributions to some things that are not of this type, it's unlikely that this sort of inequality that you use is type.
I agree, yeah. Yeah, because essentially in the inequality, I'm completely forgetting about R, therefore completely forgetting about F.
Yeah.
Okay, so then this is for the regime of shear thresholds. And now, by the way, when I say case thresholds, yeah, the type of policy I'm thinking is for certain amount of period, we set certain threshold. And then in the next period, again, for a certain amount of time, you will have another threshold and then other threshold.
So that means that if you take the, so that also fixes the TI, right?
It fixes the, for how long you will set that threshold.
But then if you get it, then you take it forever.
If you get it, you take it forever.
Oh, okay.
Yeah, so all the policies that I'm looking at with this threshold are of the type, as long as you are over the threshold, I will commit.
And are these strategies as you're showing in the picture, like they're going down, or is it the other way?
They are going down. Yeah, so, okay, now let me go to the optimal algorithm. Yeah. So for the optimal algorithm, you can show 2 things. First it's a DP. Yeah? And the DP is not complicated. So here what I'm saying is, well, if you have still t units to go, right? Then in this time, I have two possibilities, right? So either I select the value for the number of periods that are still to go, which is t, and then I will get t times xt, right? So this is what I get if I take the value until the end, okay? And the other possibility is I don't take the value, right? I let it pass. So then I will get the value once and what I would get from the next period. This is the dp. And the nice thing about the optimal solution here is that you can show that even the optimal strategy, the optimal algorithm, once you select something, you will commit until the end. So therefore, these policies are not, I mean, it's a good choice of policy.
But you have to show that before getting that that's the optimal solution, right?
I mean, yes, so you prove. Yeah. And this is something that they showed in the previous paper by others, Schmadt, yeah. And they proved that the optimal algorithm will look like this. So once you commit until the end. Good. So then this is the optimal algorithm. Okay. And now this is the idea. So now I want to understand the worst case competitive ratio for n. So I fix n. I want to understand the worst case competitive ratio when I solve the problem with n periods. This is what I want to understand. Okay.
So Victor,
Yes.
what do you mean by this strategy being optimal? You're saying that it attains this competitive ratio in that sense?
In the sense that it's the best algorithm, it's the best online algorithm.
The one that maximizes the expected value.
Yes.
Okay, it's the same statement.
Good. Then, if I want to find the worst case competitive ratio, then I have to solve this problem. Yeah, this is just an equivalent way of writing the same problem. I want to find the smallest value, epsilon n, for which if I take the value of the dp, I multiply it by 1 plus epsilon n, and I subtract the benchmark, that should be non-negative for every distribution. It's equivalent, right? So in other words, I'm saying, for example, if I multiply the value of the dp by 1.5, and if I'm able to show that that value minus the benchmark is always non-negative, then I can give a lower bound on the competitive ratio, right? Just a different way of writing the same thing, right? And then in that case, the competitive ratio will be at least 1 divided 1 plus epsilon. And therefore, if you want to maximize the ratio, you have to minimize the epsilon. And therefore, this problem is equivalent. Okay? Okay, but what is the gain here? There is some gain because now, and this is where I will do this reduction, that I will try to highlight the main ideas. This is the idea. Pick a distribution. Okay? For a given distribution, I can compute the value of the dp for each n. Right? It's like solving that recurrence, fixing the distribution. And that will give me a sequence. For every n, I have one value. And you can show that this sequence so you can show that that sequence, if you call it, say, I have f, and then from f, I will get a sequence, right, for the dp. Let me call it gn of f with n in n. That sequence will satisfy some monotonicity program.
GNFF is
It's the value of the dp, is dp, sorry.
DPF.
dpnf. dpfn. Yeah. I don't like that much notation, but I use it for the presentation because it's easier to follow. But it's DPF. Yeah. Now I keep it for every n, and this is a sequence. Okay, and then you can show that DPFN will satisfy some monotonicity properties. Let me call them A, B, and C. Okay. And now you can also prove that if I give you any sequence, satisfying A, B, and C, I can give you a distribution for which the DP sequence matches exactly that sequence. Okay? Yeah. Okay, but then this is good because now in my problem, I can reparameterize using the DP sequence. Right? I can forget about the distribution, but now I can reparameterize in terms of the sequence. Okay? And furthermore, I can show that for any distribution mapping to the same sequence for the DP, the worst in terms of the benchmark, meaning the one that will achieve the maximum value for the benchmark, is a distribution that is flat in between two consecutive values for the sequence. Yeah. So this is something called like the balayage of a distribution. So you put all the mass and you make it flat. Okay? And by making it flat and using some convexity argument, you can show that up will grow. Yeah. I'm only using convexity at some point. Yeah. But then at that point, since everything now is parameterized in terms of the sequence, you forget about the distribution. Now I have an optimization problem in the space of sequences satisfying A, B, and C. And now at that point, I already have one reduction, right? I have like an infinite dimensional optimization problem in the space of sequences satisfying A, B, and C. But then you can also show that essentially for every feasible solution in that problem, meaning any sequence satisfying A, B, and C, I can construct another sequence for which there is a point in which after that, everything is essentially constant. So I don't need to keep track of the values after that. If I know the values are up to n, then I can construct everything after that. And the value will not be worst. And therefore, now I'm going from an infinite dimensional problem to a finite dimensional problem. Now the last step.
But wait, sorry, so even if it, so you're saying it's really constant after some fixed threshold, that's not depending on n.
Not depending on n. I can give you, for any epsilon, I can construct such sequence. Yeah. But then it will work for every epsilon. So then I can take the infimum over epsilon and I will recover the same value. Yeah. But now finite dimensional. Now ABC will look different. Yeah. But now the nice thing, and this is something that happens also in other situations, like for example, if you look at the Meyerson proof, yeah, same thing here. When you optimize over the convex optimization problem, you're lucky, and it's an integer point. And therefore, you write down first order optimality condition, you have the optimal solution. I mean, of course, before that, you have to prove that the function is convex and not so easy, but you can do it. You have to work a bit, but you can do it. Yeah.
You haven't said much about the subjective function.
Yeah, exactly. So that function, after doing all these reduction that I mentioned, you will end up with something that will be convex. Yeah. And the variables that you're looking at are essentially at the final step, when you look at the finite dimensional problem, will represent the differences between consecutive optimal thresholds. So then I look at the optimal threshold when I have n to go, then I look at the optimal threshold when I have n minus 1 to go. I take the difference, and this is the meaning of the variable that I'm looking.
But I mean, it's convex and simple. Is what is polynomial or something?
No, it's not linear, but convex. I mean, You can prove convexity. Yeah.
It's like piecewise linear.
No, it's more complicated. Exactly. It's very exactly. I mean, they're not so ugly. I mean, you still can prove convexities. Not so ugly. No, but the nice thing is that when you optimize, you have an interior point. Now you write down optimality conditions, first order. You get a system, which is, it looks something like that. And that's it. And computationally, you can solve it quickly, in fact. Yeah, Pn here, yeah, that will represent a function that appears in opt when I'm writing the benchmark, but it's essentially Pn is like the summation of t to the I from I plus 1 up to n. Yeah, and from here, once you have the optimality conditions, if you take the limit, then you can make the ODE. So we select the process.
So the alphas are, what are the alphas there?
Yeah, so the alphas are representing when you write down this problem. So you have the optimal, the differences of consecutive thresholds in the optimal policy. The alphas will represent quantiles. Then I will go to the quantile space. And so the thing that if I want to go to the limit, then I prefer to be in the quantile space, because then I don't have dependency on n, right? So I have 0, 1. But this is the idea. I think that the nice thing here is the construction, like the reduction from going to the infinite dimensional problem over the distribution to a finite dimensional problem. And you're lucky enough, again, like in the proof of Myers and another thing. And my belief is that there is something deeper here. Okay, because this is not the only example I know. If you go to the profit inequality, like the classic profit inequality, I can also understand the optimal competitive ratio following the same idea. And again, I will be lucky and the optimal solution of the convex problem will be interior. So I think that there is a larger class of problem where one can show this.
But here on the distribution, you are not assuming anything, not concave,
No.
like in microphone.
Nothing.
So you don't need irony or anything.
I don't think.
So, and when you gain out of this fact that this is interior, it's just the KKT conditions are similar.
Yeah. Exactly. Yeah, the KKT conditions are similar. Yeah.
We use the insights of these policies to design something that does not require knowledge of the distribution. Because, for instance, not in this one, but in the previous example we developed, right? So you're saying, I'm only curious about setting these quantiles. That's a very rough information about the distribution, actually, right?
Yeah, I think that, probably if you allow me to make queries, right, like quantile queries.
The customers are queries.
Yeah, exactly. So I have values, so I have.
My question is, can you still get a competitive ratio guarantee in the same setting, but where you don't know what the distribution is?
You can, I think this is the data-driven setting. So I have samples, right? I don't know the distribution, but I have samples. If you have enough samples, yes, for sure. So I think that then the question is, if I have, let's say, only constantly many samples per value.
But I think it's, okay, maybe you're right, but like the question still makes sense, like.
But what is the access?
Insufficiently large is not necessarily, yeah, if you get, okay, one over epsilon samples, you can learn the distribution, but are you gonna waste all those samples because you're do better?
Or
I think that's still gonna affect the competitive ratio.
Yeah, no, it does, it does. So I think that you will lose a bit because of the approximation. But still you can do, I mean, if you have sufficiently many, you can do well. Yeah, but if you have only a few, then no, I mean, there is an impossibility. I mean, at least for the classic profit inequality, there is an impossibility. But you need at least linear limit. Here, I haven't thought much about it, but I guess something similar would be true. The data-driven setting. Yeah, and just to finish, because I think I'm over the time. Yeah. Let me skip this thing. You can say something about the secretary version. I will keep it. And yeah, and essentially, you know, like one thing, next question would be to understand this ODE. Yeah, try to prove that it's one over the golden ratio. I couldn't manage that. I think it is true. Yeah, and of course, you can try to understand other different settings. For example, now you can say, well, what happens if the distributions are not IID? That's open. If the distributions are non-identical. And now the complicated thing is that if the distributions are non-IID, you not necessarily will commit until the end. It might be good to only commit for a few number of years. And therefore, the optimal policy will be a bit more complicated, but it's okay. Yeah, that's it. Thank you.
Questions? Other question for us?
So solving this question about the ODE implies that the optimal competitive ratio is 1/5. That's
Yes, it will be. So the thing that computationally, I can tell you now that
it's
is
close to that.
up to 10 to the -6. But I would like to prove that it's one over the and because it's nice. I think the golden ratio. It had to be true. I didn't find the proof when it should be true.
Any other questions? Okay, well, let's thank Victor.